Hello everyone, and welcome to a little video which will explain how things drive in circles. So we're going to do two examples here today. The first one, 1,200 kilogram car driving around a circular portion of road of radius 65 meters at a constant speed of 15 meters per second, as in the diagram below. Now, one thing about the diagram, couple things actually. First of all, you're looking down on this from above right here. Okay? And secondly, it is not at all to scale. That is not 65 meters compared to the width of a car. Okay? Just trying to make it so you can see it. Now, what I want to know in this problem is what is the minimum coefficient of static friction required to keep the car on the road? So as with most things that we've done in this unit, we're going to start out by drawing a force diagram. However, we are not going to draw the force diagram from the perspective of this. Instead, and you'll see why in a moment, we're going to draw the force diagram as if the car is coming out of the screen and turning to your right. Okay, so in other words, take this and kind of tilt it so that you're looking at its face. Okay, so here's the car. Now, what forces act on the car? Well, of course, it is interacting with the earth with a force of gravity. It's being supported by the road surface, which would be a normal force, which would act upward. Since it's not accelerating up and down, that normal force would balance out the force of gravity. Now, there is one more force here, and this is a force which needs to point inward, right, inward, in order to make the car move in a circle. So think about what the force is that would stop you from sliding tangent off the road. That force would, of course, be friction. Now, you might wonder, why is it static friction? Well, I'm being kind of technical there. It's really because of the rolling tires. If you consider rolling tires, if they're rolling without slipping, then the bottom of the tire is actually considered to be at rest with the road. I know that sounds strange, but consider if you lock your tires up. Right? If you can lock your tires up, then the tire surface would slide across the road, and you'd have kinetic friction. It's one of the advantages of using anti-lock brakes is that it keeps your tires rolling so that you end up using static friction instead of kinetic friction. And if you remember from our friction labs, static friction is bigger. So you actually have more control over the car that way when you keep the tires rolling. Now, if we're going to find the minimum coefficient of static friction, that's going to be inside of static friction. So let's look at the horizontal force situation here. First of all, notice that it's unbalanced, right, and therefore it is accelerating. So, by Newton's second law, the net horizontal force must be equal to its mass times its acceleration. Now, there is only one horizontal force, and in our diagram, the force of static friction is to the right, so positive. This thing would be accelerating inward, which of course is also to the right, which would make it positive. And this is not just any acceleration. This is the acceleration of an object moving in a circle at a constant speed, which is the centripetal acceleration. So our net force is just the static friction, and our acceleration is the centripetal acceleration, and it's positive. Now, since we're looking for the minimum coefficient of static friction, that would occur when you're using all of the static friction. Remember, static friction goes anywhere from 0 to a maximum. So the maximum amount of static friction can be found by taking the coefficient of static friction times the normal force. So this is what we're actually trying to find in this problem. Also remember that we can calculate the centripetal acceleration with speed squared over radius. So that can go right there. Plug them both in. You get the coefficient of static friction times the normal force equals the mass times the speed squared over the radius. Now, we know everything in here except the normal force, but remember, because it's not accelerating up and down, the normal force equals the force of gravity, and the force of gravity is, of course, mass times gravitational field strength. Plug that into our equation, and we get the coefficient of static friction times the mass times the gravitational field strength equals the mass times the speed squared over the radius. And notice, the masses cancel. Now this is kind of interesting because it means that it doesn't matter whether it's a motorcycle or an 18-wheel truck going around this curve. If they want to go around the same radius curve at the same speed, then mass doesn't matter. Right? They're all going to be at the same speed. Now why is that? Well, it's because more mass means more gravity, which means more normal force, which means more friction. And not only is there more friction trying to keep you on the road, but there's also more mass in the MA, which means there's a greater amount of inertia, which is trying to take you tangent. So these things cancel out because they're all proportional. Finish up the problem here. We need to divide by g, right, to get mu s by itself. And by the way, at this point, you could really solve for anything. If I gave you the coefficient, you could solve for the required speed, which would be what they would do on a road if they were going to put one of those little yellow signs where they tell you, you know, this is the suggested speed. And they would do this kind of analysis, assuming they knew the coefficient of static friction between the tires and the road. Plug in your numbers. Work it out, and you'll see all the units will cancel. And you get a minimum coefficient of static friction of 0.35. So if the coefficient between the rubber tires and the road is more than 0.35, you're good to go. Right? You can go at that speed at 15 meters per second, which is, by the way, about, I don't know, maybe 35, 40 miles an hour, right? And you won't slide off of the road. Now, in some cases, of course, the road is either has such a small radius, or you might be moving at such a high speed, like, for example, an off-ramp on a highway that's a circle, where both of those might be true. You might be going at a high speed on a pretty tight curve, that they don't just build a flat road. Right? What do they build? Think about going on off-ramps here. What they do is they bank the road. So let's look at a problem like that. Here is a circular curve of highway designed for traffic moving at 60 kilometers per hour. The radius of the circle is 150 meters. Again, the diagram is not drawn to scale. This time I want to know what angle must they bank the road for it to successfully negotiate the road with no friction. Now, the reason we're doing it with no friction is that's kind of the slowest speed then, or the biggest angle you would need. Right? Because if you had friction, friction would help keep you on the road like it did in the last problem. So here we're doing this as if, let's say the off-ramp is completely icy. It's a winter day in Michigan. And so you hit that road. If you're going at 60 kilometers per hour and the road is banked at the angle we're about to find, you would simply slide around the curve. You wouldn't slide off the road, which would kind of be a cool thing, but it's kind of a safety thing then. Now, just like we did last time, we're going to draw we're not going to use the diagram exactly. We're going to draw this as if it's coming out of the screen at us. So there it is. Now you might wonder, why is this car on a hill? Well, it's not really on a hill. This is the banked road, right? So this is, if you will, a cross-section of the road. It's actually coming out of the screen and turning to our right. So tilt this up again so that it's pointing right at you, right? Hopefully you can see that. And theta, this little angle right here, is the angle of banking. That's what we're trying to find in this problem. So, there's the car. Now, you might be tempted to rotate our axes, because that's what we always did before when we were on an incline. But this is kind of a different problem, because unlike when we did these before where you were going up and down the incline, here you're actually moving around the curve in a horizontal circle. So, we're not going to rotate the axes. We're going to leave them horizontal and vertical. And again, that's because we want the acceleration to be one-dimensional. The acceleration is going to be inward. It'll be horizontal because you're moving in a horizontal circle. So you're not sliding up and down the hill, which was when we would rotate the axes. Since we're leaving our axes this way, there is now a force acting on the car, which is not just horizontal or vertical. It's a little bit of both. And that force would be the normal force, the support force from the road on the car. Remember, normal means perpendicular. So the normal force here is going to act perpendicular to the surfaces. Since it's not on an axis, we need to break it up into vertical component and horizontal component, and notice the little angle is right there. That's how much the angle of the road, is banked. Right? Should be able to see that from the diagram. Now, there also is a force of gravity acting on the car, which, of course, as gravity always does, acts straight down. Notice that since it's moving in a horizontal circle, it is not accelerating vertically. And since it isn't accelerating vertically, f of g has to balance out f of ny. Notice nothing is balancing out the x component of the normal force, and therefore it provides the centripetal force needed to keep you moving in a circle. And notice its direction. It's pointing inward to the circle. And the car, of course, would therefore be accelerating inward, right, towards the center of the circle. Okay, here comes the fun part, the math. First of all, vertically, the normal force y component has to balance out the force of gravity because it's not accelerating up and down, Newton's first law. F of ny then would be equal to m times g. Now, before we go any further, let's take a look at the horizontal part. Horizontally, it is accelerating. As we talked about, it is accelerating inward to the right. So, since it is accelerating horizontally, it must have a net force horizontally, and by Newton's second law, that net force must equal mass times acceleration. Now, there's only one horizontal force, that's F of nx, it's to the right. And let's see here, the acceleration is also inward, which is to the right, so it's positive. And it's not just any acceleration. This is the inward directed acceleration of an object moving in a circle at a constant speed. It is the centripetal acceleration. F of nx, right, is equal to positive mac. Now, this next little bit's probably not going to be obvious, but you'll see why I'm going to do this in a moment. Okay, AC, remember, is speed squared over the radius. I didn't show that substitution, but hopefully by now you realize that you can make that substitution. Now, I'm going to look at the tangent of this angle. You'll see why in a second. Tangent of this angle is opposite side over adjacent side. So it is f of nx over f of ny. Move f of ny over here, and you get f of nx is f of ny tangent of theta. Substitute that in. We get f of ny tangent of theta equals mass times speed squared over the radius. Now, why the heck did I make that conversion? Because we know what f of ny is. It's equal to the force of gravity, or mg. And so we can plug it in right there. That gives us mg times the tangent of theta is mv squared over r. And like the first problem, the mass cancels. More mass means more inertia trying to take you off tangent, but more mass also means a bigger normal force, more gravity, which is trying to push you in and keep you moving in a circle. And since everything is proportional, those two things cancel out. This means that when they design the road, they don't have to design a different angle depending on what kind of auto is driving on it, depending on whether it's a motorcycle or a car or an 18-wheeler. All of them would slide around the curve the same way with no friction. Divide both sides by g, and you get an equation that I'm going to box in for you. That means I want you to keep it, if you remember. I don't want you to have to go through this process again for this kind of problem. There might be like one problem or something on the test that will be asking about a banked road. So if you have this equation on your card, you can just use it. And with this equation, you can solve for anything. Right? Given three of the variables, you can solve for the fourth. Now, in this case, we're trying to find the angle. So I don't want to know the tangent of the angle. I want to know the angle. So the way you do that is by taking an inverse tangent, right, of the right-hand side. So theta would be the inverse tangent of speed squared over the radius times the gravitational field strength. Now, before we just willy-nilly throw our numbers in there, we've got an issue. And our issue is this. Yeah, if we were in Canada, this is what the road sign would say, 60 kilometers per hour. But that's not going to work in our problem because we have the radius in meters, so we can't have meters in kilometers. And remember, g, the gravitational field strength, is in newtons per kilogram, and so that's not going to work with kilometers per hour. So we're going to have to do a little conversion here, which I'm sure you'll enjoy. To switch kilometers to meters, there are 1,000 meters in 1 kilometer. To switch hours to seconds, there are 3,600 seconds in 1 hour. 60 minutes times 60 seconds in each minute. Right? So 60 times 60 is 3,600. Now, if you wonder why I wrote them that way, remember I'm basically multiplying by 1, so I'm not changing anything. I'm just converting the units. And I wrote them this way so that the units would cancel. The kilometers on top cancel with the kilometers on bottom. The hours on bottom cancel with the hours on top. So if you take 60 times 1,000 divided by 3,600, you get about 16.67 meters per second. Plug all those numbers into the equation. Be careful that you put parentheses around things, so you have to calculate this first, then take the inverse tangent. And you get a reasonable angle of 11 degrees. So if this curve is banked at 11 degrees, and you hit it going 60 kilometers per hour, and there's no friction at all, you ought to be able to just slide around the curve and come out the other side. If there's friction, which there will be in most cases, friction will help you, like you saw in example 1, and then you could go even faster. So I hope you've enjoyed learning about driving in circles.